A proton is 100,000 times smaller than an atom. Quarks are smaller still, and below quarks, there is a gap so enormous it makes every scale above it look like nothing. At the very bottom sits the Planck length, 1.6 times 10 to the negative 35th meters. The place where space stops being smooth, where time loses all meaning, and where our two greatest theories of physics shatter against each other. We are going there. We will descend through quantum foam, survive a black hole hotter than any temperature in physics, watch space-time bounce before the Big Bang, and confront the possibility that everything around you is a hologram. Like and subscribe if you want to come with us. We begin. Your hand is in front of you right now. Look at it. The skin, the lines, the texture. You can see all of it. But look closer, and the familiar dissolves. Past the scale of what your eyes can reach, past the cells packed like tiles under your skin, past the molecules that hold those cells together, past the atoms at the heart of every molecule. Zoom to the center of one of those atoms, to the tiny, dense nucleus rattling around inside a vast cloud of empty space. Then deeper still, into the nucleus itself, down to the protons and neutrons, and further into those, down to quarks, the smallest things science has ever directly detected. Most people who have heard of quarks assume that is the bottom, that there is nothing smaller, that the journey ends there. It does not end there, not even close. Below the scale of a quark, there is a gap, a plunging, almost incomprehensible drop through levels of smallness that dwarf every distance we just crossed. The gap between a quark and the floor of that journey is wider, by some measures, than the gap between a quark and a city. And at the bottom of that gap, something waits. Physicists are not sure what it is. They are not sure whether the word something even applies down there in any normal sense. What they do know is this: there is a scale, a specific calculable distance, where every theory we have breaks, where the mathematics of physics stops working, where space and time, as we understand them, may cease to exist in any recognizable form. That distance has a name. It is called the Planck length, and it sits 20 orders of magnitude below the scale of a quark. To put that in terms you can feel, if you took a single proton and expanded it to the distance across a galaxy 1,000 light-years wide, the Planck length in that same scaling would be about the width of a human hair. The gap is that staggering. For most of human history, the question, how small can things get, was purely philosophical. Democritus debated it in ancient Greece. Newton assumed space was infinitely divisible. Einstein built his greatest theory on a smooth, continuous geometry that could, in principle, be sliced finer and finer forever. Nobody thought there was a flaw. But there are clues that the flaw exists, that reality has a resolution limit the way a photograph has a pixel count. And the evidence for that flaw did not come from a particle accelerator. It came from a mathematician's notepad in Berlin, in the year 1899, from a man who was trying to solve a completely different problem. He was trying to figure out why metal glows red when you heat it. What he found instead was a number, a very strange number, a number that did not belong to any human unit system, did not depend on any arbitrary convention, and could not be made to go away. A number that, 125 years later, physicists still cannot fully explain. And when you look at what that number points to, at the implications that fall out of it like dominoes, the question shifts from how small can things get to something far more unsettling. The question becomes, does space exist at all at the smallest scale? Berlin, 1899. Max Planck was a meticulous, methodical physicist, the kind of man who trusted mathematics the way others trust solid ground. He was solving an engineering problem, not chasing deep truths about the fabric of reality. The problem was this: Physicists knew that when you heat any object, an iron poker, a ceramic bowl, a lump of coal, it glows. First dull red, then orange, then white hot as the temperature climbs. The color tells you the temperature. Simple enough. But every equation written to predict that glow gave the wrong answer at short wavelengths. The predictions spiraled toward infinity. The models were broken, and nobody knew why. Planck fixed it. He introduced a new constant into physics, a tiny number describing the minimum chunk of energy that could be exchanged between light and matter. The constant made the equations work. He called it h. We now call it Planck's constant, and it is one of the most important numbers in all of science. But Planck noticed something in that same paper, almost as an aside. He had his new constant. Physics already knew two others. One was Newton's gravitational constant, pulled from centuries of work on falling objects and orbiting worlds. The other was the speed of light, measured with precision by that point. These three constants came from entirely different corners of physics. One governed how matter attracts matter across vast distances. One governed the rules of light and motion through space and time. One governed how energy moves in the quantum world. They had, as far as anyone knew, nothing to do with each other. Planck combined them anyway. He just wanted to see what units would fall out. The combination produced something unexpected. There was exactly one way to multiply and divide those three numbers that produced a measurement of length. One arrangement. And the length it gave was roughly 1.6 times 10 to the minus 35 meters. A number so small it defies immediate comprehension. What made Planck pause was the independence of the number. This length did not depend on any human choice. The meter is a human invention, originally tied to the circumference of the Earth. The kilogram was defined by the mass of a particular metal cylinder locked in a vault outside Paris. The second is rooted in the rotation of a planet. Every unit in science is, at bottom, a human convention. This length fell out of nature's own equations, clean and unavoidable. Planck flagged it in a footnote as remarkable. He wrote that this length, and the family of units it belonged to, would retain their meaning for any civilization anywhere in the universe. He did not know why. He had no theory to explain it. He was doing dimensional analysis, the physicist's version of seeing what fits. And what fit was a number that pointed, as it turned out, to the exact scale where all of physics collides with itself. Nobody paid much attention to that footnote for decades. It was a curiosity, a mathematical coincidence. The tools to understand what it meant did not yet exist, but the number was patient. So what is it, exactly, that makes three unrelated constants from three different branches of physics combine to produce one specific, physically meaningful length? That is where things get interesting. Picture three kingdoms, each governed by its own laws, each ruling a completely different territory. The first kingdom governs the very large. It rules how galaxies spiral, how planets orbit, how mass pulls on mass across distances measured in millions of light years. Its master key is Newton's gravitational constant, the number that tells you exactly how strong gravity is. Call it G. The second kingdom governs the very small, atoms, electrons, photons, the quantum behavior of particles that exist in multiple states at once and share information across vast distances. The master key here is Planck's constant, the number defining the smallest possible chunk of action in the universe. Call it h bar. The third kingdom governs motion and light. It sets the absolute speed limit of the universe, the wall that nothing carrying information can ever breach. The master key is the speed of light. Call it c. These three kingdoms, for most of the history of physics, were separate countries. Electron orbits required no knowledge of gravity. Comet trajectories required no knowledge of quantum energy packets. The gravitational pull between two stationary objects required no knowledge of the speed of light. Each domain handled its own business. That was fine. Here is the remarkable thing. When you take those three constants and ask, what length can be constructed by combining them, the answer is unique. There is exactly one arrangement that produces a unit of distance. One combination of g, h bar, and c that gives you meters rather than seconds, kilograms, or some dimensionless number. And the length that falls out of that one combination is the Planck length. This matters more than it might seem. The fact that a unique length emerges from combining these three constants is the universe signaling something. It is pointing at a scale where all three kingdoms must be considered simultaneously, where you cannot ignore gravity, cannot ignore quantum mechanics, cannot ignore relativity. Every other scale in physics lets you pick two and discard the third. At the Planck scale, all three arrive at once, with equal force. Think about what that means. General relativity, the theory of gravity, describes how space and time warp in response to energy and mass. Quantum mechanics describes how energy and matter behave in wildly uncertain probabilistic ways. These two theories have been the twin giants of modern physics for a century, each tested to a precision that would astonish earlier generations of scientists. At every scale above the Planck length, you can use one or the other and get correct answers. Build a bridge, use Newtonian gravity, ignore quantum mechanics. Describe an electron, use quantum mechanics, ignore gravity. The separation works beautifully. At the Planck length, that separation becomes impossible. The energy fluctuations demanded by quantum mechanics are powerful enough to curve spacetime dramatically. The curvature of spacetime is violent enough to affect quantum behavior fundamentally. You cannot turn either theory off. They must both apply at the same time. And here is the crisis lurking in that fact. These two theories are built on assumptions that directly contradict each other. Physicists have known this for nearly a century, and it has never stopped bothering them. What actually happens when both theories are forced to apply at the same scale is the most dangerous question in all of physics. But before we can understand what breaks, we need to feel how far down the Planck scale actually is, because the number alone will not do it. Before we go deeper theoretically, we need to make the distance real. Numbers like 10 to the minus 35 meters land in the brain as empty syllables. The mind files them under very small and moves on. That is not good enough here, because the absurdity of this scale is part of what makes the physics so strange. A proton is already extraordinarily small. You could line up roughly 10 million of them across the width of a single human hair. The proton is the dense core at the heart of every hydrogen atom, and to probe its structure required building a machine the size of a city, one that smashes particles together with colossal energy just to glimpse the debris. Even that machine only reaches down to proton-scale distances. The Planck length sits 20 orders of magnitude below the proton. That is 100 quintillion times smaller than a proton. The ratio between the Planck length and a proton is roughly the same as the ratio between a proton and 1,000 kilometers of open road. Here is another way to feel it. Take a single hydrogen atom and imagine expanding it until it fills the observable universe. The observable universe is a sphere roughly 93 billion light-years across. In that expanded atom, where electrons orbit at cosmic distances and the nucleus has grown to the size of a solar system, the Planck length would scale up to roughly the size of a grain of sand. One grain of sand inside a sphere 93 billion light-years wide. Every particle accelerator ever built by humanity probes distances that, on this scale, remain enormous. The Large Hadron Collider, outside Geneva, buried in a circular tunnel 27 kilometers around, accelerates protons to within a fraction of a percent of the speed of light and smashes them together with the highest energies ever achieved in a laboratory. It probes distances roughly 1,000th the size of a proton. Extraordinary. And that is still 16 quadrillion times larger than the Planck scale. To approach Planck energies with a circular accelerator would require a ring of magnets running for roughly 100,000 light years, comparable to the diameter of the Milky Way galaxy. And even that likely would not be sufficient, because at those energies, the physics of the machine itself would fail. The wall here is built into the structure of how quantum mechanics and gravity interact together, which raises an immediate and uncomfortable question. If the Planck scale is this absurdly unreachable, how does anyone know anything about it? What is the point of calling it the fundamental scale of physics if no one can look at it directly? The answer is where science gets genuinely interesting. Everything we know about the Planck scale comes from mathematics, from following our best theories to their logical conclusions and watching what falls apart. The theories point at the Planck scale the way shadows point at a source of light. You cannot touch the source, but the shadows tell you where it is. And what the theories say is waiting at that scale is considerably stranger than most people ever suspect. What Planck discovered in 1899 extended far beyond a tote, single length. The same three constants produce an entire family of extreme values, each one a window into just how alien the Planck scale is from anything physics has ever studied. Start with the Planck mass. The result is roughly 22 micrograms. 22 millionths of a gram. That sounds tiny. In daily life, it is. But in particle physics, it is enormous. A proton weighs about 1.7 times 10 to the minus 24 grams. The Planck mass is about 10 billion times heavier than a proton. By particle physics standards, it is roughly the mass of a flea egg. Yet, if that mass were compressed into a Planck scale volume, it would form the smallest black hole theoretically possible, an object where gravitational energy and quantum mechanical energy become exactly equal. One concept from each kingdom, perfectly balanced, in a speck smaller than an atom. The energy equivalent of the Planck mass, calculated using Einstein's relationship between mass and energy. The result is roughly 2 billion joules. That is about the kinetic energy of a fast-moving car, unremarkable on a highway. Compressed into a single particle, it is roughly 10 million billion times more energetic than anything the Large Hadron Collider has ever produced. The universe has not seen individual particles carrying that much energy since its very first moments of existence. The Planck temperature follows from this. At the Planck scale, the thermal energy equivalent reaches roughly 100 million trillion degrees above absolute zero. The core of the star at the center of our solar system burns at around 15 million degrees. The Planck temperature exceeds that by a factor of 10 trillion. At this heat, every known concept in thermodynamics simply dissolves. Then comes the Planck density, the amount of mass squeezed into a single Planck scale cube. The number is roughly 5 times 10 to the 96th kilograms per cubic meter. Water is 1,000 kilograms per cubic meter. A neutron star, one of the densest objects in the observable universe, packs in around 100 quadrillion kilograms per cubic meter. The Planck density exceeds even neutron star density by a factor so enormous that all the mass of the observable universe, every galaxy, every star, every wisp of gas between them, compressed into a single Planck-sized volume, would still fall short. These values are boundary markers, the thresholds at which the equations of physics formally stop working and start returning nonsense. Together, this family of extreme values paints a portrait of a regime so far outside human experience that even the conceptual tools we use to think about physics may not survive the crossing. And the two most powerful tools humanity has ever built for understanding the physical world are heading toward that boundary on a collision course with each other. One describes everything large, the other describes everything small. Each has never been wrong in its own domain. Each carries an assumption that makes the other impossible. For the past 100 years, physics has rested on two extraordinary achievements. One describes the very large, the other describes the very small. Together they have never been wrong in their own domains. Separately, they are the most precisely tested theories in all of human knowledge. The problem is that they are built on assumptions that flatly contradict each other. General relativity is Einstein's masterpiece. It describes gravity as the curvature of space-time, a fabric that bends and warps in response to mass and energy. A planet does not orbit a star because a force yanks it sideways. It follows a curved path through a curved geometry, the way a marble rolls along the surface of a stretched rubber sheet. Every prediction general relativity has ever made has been confirmed. The bending of light around massive objects, the slowing of clocks near strong gravitational fields, gravitational waves rippling across space from colliding black holes. All confirmed, all precise, all matching the equations. General relativity requires space-time to be smooth. Its equations are differential equations, which means they need the fabric of space and time to be continuous, infinitely divisible, always well-defined. Without a smooth geometry, there are no derivatives. Without derivatives, there is no theory. Quantum mechanics is the other giant. It governs particles, atoms, light, and the fundamental forces at small scales. It tells us that particles have no definite positions until measured, that energy comes in discrete chunks, that two particles can be entangled such that measuring one instantly determines the state of the other regardless of the distance between them. Every prediction quantum mechanics has ever made has also been confirmed, with the quantum theory of electromagnetism ranking as the most precisely verified prediction in all of science. Quantum mechanics requires a fixed, stable stage. Its equations describe how particles evolve through time, but time in those equations is an external backdrop, a smooth river that keeps flowing regardless of what the particles are doing. The stage does not react to the actors on it. Here is the contradiction. General relativity says space-time is dynamic. It bends, it stretches, it participates actively in the physics, shaped by the matter and energy within it. Quantum mechanics says space-time is a passive background. It cannot participate. It just is. These two assumptions cannot both be true at the same time, in the same situation. At scales where both gravity and quantum effects are small relative to each other, the contradiction does not surface. The theories sit in their separate domains and never have to confront each other directly. At the Planck scale, they cannot avoid each other. Energy at this scale is so extreme that gravitational effects are enormous and quantum effects are equally enormous, and each is affecting the same tiny region of space at the same instant. Applying general relativity gives one answer. Applying quantum mechanics gives another. Applying both simultaneously produces equations filled with infinities that no known mathematical technique can resolve. At the Planck scale, physics as currently written is demonstrably broken. Physicists have known this for decades, and the attempt to repair it has a particular shape of failure that is worth understanding in detail. Every quantum field theory physicists have written down began as a disaster. When you calculate using any quantum theory, you must account for all the ways virtual particles can pop in and out of existence during any given interaction. An electron moving through space does not simply travel in a straight line. At the quantum level, it constantly emits and reabsorbs photons. Pairs of particles and their antimatter counterparts flicker briefly into existence and annihilate, and these processes repeat at every scale of energy, including infinitely high ones. When you add up all those contributions mathematically, they sum to infinity. For the early quantum theorists, this was a catastrophe. Their equations returned nonsense. A particle that should have a specific, measurable mass or charge came back with an infinite value. The resolution was a technique called renormalization. The essential idea is this. The infinities that appear in the calculations are the right kind of infinities. They can be systematically absorbed into the measured values of physical constants, the mass of the electron, the charge of the electron, and so on. You calibrate the calculation at one energy scale by measuring those quantities there, and the infinities cancel out everywhere else. The theory becomes finite, predictive, extraordinarily accurate. Renormalization works for the quantum theory of electromagnetism. It works for the quantum theories of the strong and weak nuclear forces. It works for essentially every quantum field theory describing the particles and forces of the Standard Model. These are the theories that account for virtually everything observable in particle physics experiments. Gravity refuses to cooperate. When physicists treat gravity as a quantum field theory, with gravitons as the force-carrying particles, and attempt to apply renormalization, the infinities multiply in a specific and catastrophic way. Each attempt to absorb them requires introducing new parameters. Those new parameters generate new infinities at higher energies. Absorbing those creates more new parameters, which generate more infinities. The process never converges. You would need an infinite number of parameters, each set by a separate experiment, to tame the theory. A theory requiring infinite inputs predicts nothing. The physical meaning of this is worth sitting with. Renormalization works because physics at large scales is largely insensitive to what is happening at very small scales. The behavior of an electron does not depend sensitively on virtual particles flickering at a billion times higher energy. The theory is forgiving of what happens at short distances. Gravity is different. Gravity is self-reinforcing. Gravitons carry energy. Energy generates gravity. So gravitons themselves generate more gravitons, and the feedback amplifies without limit as energies climb. At the Planck scale, that feedback peaks. The self-reinforcing nature of gravity spirals beyond any known mechanism of control, and every calculation of every physical quantity returns infinity. Something must happen at the Planck scale that we have no equations for. Something must replace the smooth space-time picture before the mathematics explodes. A physicist at Princeton once had a vivid and almost hallucinatory image of what that something might look like. He thought about it for years, and what he imagined was not a particle or a field. He imagined foam. John Wheeler was the kind of physicist who thought in images. He coined the term black hole. He helped build the first American nuclear reactor alongside Enrico Fermi. He spent years as Einstein's colleague at Princeton. In the mid-1950s, he turned his attention to the deepest question he could find. What is the actual structure of space at the very smallest scale? Most people learn it as a statement about position and momentum. You cannot know both precisely at the same time. But the uncertainty principle is far more general. It applies to any pair of conjugate quantities in physics, including energy and time. The shorter the time interval you examine, the more uncertain the energy in that interval must be. The uncertainty is a statement about what physically exists, independent of any instrument. Now apply that to space-time itself. General relativity says energy and mass curve space-time. The more energy in a region, the more that region curves. Quantum mechanics says energy is uncertain at small scales and short times. If energy is uncertain, the curvature of space-time must also be uncertain. At large scales, this effect is immeasurably small. The geometry is effectively stable. The entire apparatus of classical physics, including the concept of a well-defined location, works just fine. Zoom toward the Planck scale and the uncertainty in curvature grows with every step. Wheeler calculated what happens when you reach the Planck length. The result was extraordinary. At that scale, the uncertainty in the curvature of space-time becomes comparable to the curvature itself. The geometry churns violently. The stage on which all of physics is performed does not hold a fixed shape. Wheeler called this quantum foam. Imagine the ocean surface from a great height, smooth, calm, reflective. Now, imagine it from the surface during a storm, heaving swells, breaking whitecaps, spray. Now imagine it from the perspective of a single water molecule. No surface at all, just chaos. Wheeler's picture of the Planck scale was that third image. The fabric of space, at that depth, is a turbulent, seething froth of topological fluctuations. Microscopic wormholes forming and dissolving before anything could pass through them. Regions where the very shape of space is temporarily knotted, tunnels through geometry that pinch off faster than any clock could register. Wheeler was making a rigorous physical argument, grounded directly in the mathematics of quantum mechanics and general relativity. The uncertainty principle, applied to space-time geometry rather than particle position, forces this conclusion. Space at the Planck scale is an active, churning medium. Wheeler published this picture in the 1950s. It has never been directly confirmed because no instrument can reach those scales. But every serious approach to quantum gravity since then has had to engage with it. Some theories produce quantum foam naturally. Others attempt to work around it. None can simply ignore it. And the foam creates a problem that goes far beyond geometry becoming turbulent. If space-time is genuinely foaming at the Planck scale, something deeper starts to unravel. The foam goes further than complicating measurements. It attacks the meaning of location itself. When you point at something, you are relying on a vast, invisible infrastructure. The concept of here requires a fixed geometric stage, a background space with well-defined points, stable distances between them, a reliable relationship between any two locations. You can say that chair is 2 meters away only because the space between you and the chair has a consistent, definite geometry. Move a ruler from here to there and back, and it returns the same length. The geometry does not change while you measure it. Take that stable background away, and here becomes meaningless. The uncertainty principle applied to space-time geometry is what takes it away. Energy is uncertain at small scales. Energy curves space. The geometry of space is therefore uncertain. At scales well above the Planck length, this uncertainty is so tiny it plays no physical role. The stage is effectively stable. Below the Planck length, something fundamental breaks. The uncertainty in the position of a point in space becomes comparable to the Planck length itself. Two locations, separated by less than a Planck length, do not have a well-defined relationship with each other. The distance between them jitters. The geometry that would let you say, this point is here and that point is there, and the distance between them is exactly this, does not hold still. A perfect ruler and a perfect eye would find the same result. The geometry itself is uncertain, and geometry is the foundation that location is built on. Strip out the geometry, and the concept of location goes with it. Physicists describe this as the breakdown of the space-time manifold. A manifold is the mathematical object representing smooth, continuous space, the kind where calculus works and straight lines have well-defined lengths. At the Planck scale, the conditions needed for a manifold to exist are no longer satisfied. The manifold is replaced by something else, something the equations of general relativity have no language to describe. The closest image might be trying to identify a specific wave on a stormy sea. Individual waves exist for a moment, have a position for a moment, and then dissolve back into the turbulence. At the Planck scale, the fabric of space is the stormy sea, and every location is a temporary eddy rather than a fixed point on a coordinate grid. The implications cascade outward from this. Cause and effect depend on location. One event causes another only if the first lies in the causal past of the second, which requires well-defined space-time positions. begin to dissolve those positions, and the structure of causality blurs. Nearby events stop having clearly defined sequences. The logic of this happened, then that happened, needs a stable geometric foundation that the Planck scale does not provide, and if location dissolves, time is the obvious next casualty. Time and space in Einstein's framework are woven together into a single geometric entity. If the geometry loses coherence at the Planck scale, then when comes under the same pressure as where. The mathematics of quantum gravity suggests that time, at this scale, does something genuinely alarming. Somewhere inside every equation of classical physics sits the letter T, time. It flows from left to right across every formula: a pendulum's position, a planet's orbit, a particle's velocity. All are functions of T, all described as things that change as the clock ticks. Time was the river everything else flowed through. External, absolute, ticking regardless of what the physical system was doing. Quantum mechanics kept time in this role. Schrödinger's famous wave equation describes how a quantum state evolves, but time in that equation is an external parameter, a backdrop provided from outside. Even in special relativity, where space and time merge into a single four-dimensional fabric, each observer still carries a well-defined clock threading through their own time coordinate. In the 1960s, physicists John Wheeler and Bryce DeWitt attempted the most ambitious calculation in the history of physics. They tried to write the Schrödinger equation for the entire universe. The result would be a wave function not for a single particle, but for all of space-time geometry at once. The equation they produced is called the Wheeler-DeWitt equation. It is still considered one of the most important starting points for quantum gravity research, and it contains a feature so strange that physicists have spent decades arguing about whether it is a clue or a catastrophe. Time does not appear in it. The Wheeler-DeWitt equation describes the quantum state of the universe as a wave function defined across the space of all possible three-dimensional geometries. There is no variable t. There is no clock ticking in the background. The equation does not describe how things change over time. It is a constraint equation, saying that the physical states of the universe must satisfy a certain relationship, a relationship frozen in place, with no temporal flow built in anywhere. The universe described by Wheeler-DeWitt is not evolving. It exists in a superposition of all its possible configurations simultaneously, without any moment being before or after any other. What we experience as the passage of time, the relentless forward march from past to future, does not appear in the fundamental equation at all. This is the problem of time in quantum gravity, and it is one of the deepest unsolved puzzles in physics. The emerging picture suggests that time as experienced is emergent. It arises because large subsystems of the universe become correlated with each other in ways that produce the appearance of temporal sequence. A rock becomes more weathered, a cell divides, a memory forms. These correlations, accumulating between vast collections of atoms, generate the sensation of time's passage, the same way the pressure of a gas emerges from the collective motion of individual molecules. At the Planck scale, those correlations are absent. There is no before and no after, only a timeless superposition of all possible geometric configurations at once. This is a profound and disorienting picture. The most basic feature of human experience, the sense that the present is real and the future is open, may be a high-level approximation emerging from a substrate where time does not fundamentally exist, but even this is not the deepest question. The deepest question is whether spacetime itself, time and space woven together, is fundamental at all. One answer to that question has been building for decades, and it involves something almost as surprising as the answer to matter's structure was when we first learned about atoms. The possibility of atoms of space. Ask a physicist whether space-time is continuous or discrete, and you will not get a quick answer. You will get a long pause, followed by a careful explanation of why the question matters enormously and why it remains completely unresolved. The question goes like this. Matter, it turned out, is discrete. The ancient Greeks guessed it. Modern physics confirmed it. Break down any material far enough and you reach atoms, and atoms are made of electrons and quarks, and below those there appears to be nothing further that divides in the same way. Matter has a granular, irreducible structure. What about space itself? Is space infinitely divisible? Can you always find a point halfway between two other points, without limit, forever? Or does space also have a granular structure, a minimum chunk below which the concept of in-between loses meaning? General relativity, the theory that currently governs our best understanding of space and time, assumes infinite divisibility. Space-time in general relativity is a smooth mathematical manifold built on the framework of calculus. Every equation in the theory requires derivatives, which require limits, which require the ability to zoom in infinitely close. Strip out continuity, and the entire mathematical structure collapses. The case for discrete spacetime comes from several directions at once. The first is the argument from the previous chapters. If space is foaming and churning at the Planck scale, if position loses meaning there, then halfway between two Planck-separated points may simply be nowhere. The smooth manifold assumption may be a brilliant approximation at large scales and a fiction at the smallest ones. The second direction comes from black hole physics. Physicists discovered that the maximum information content of any region of space is proportional to the area of its boundary. Measured in units of the Planck area, each patch of surface, 1 Planck area in size, encodes exactly 1 bit of information. A truly continuous spacetime could hold infinite information in any finite region, no matter how small. The information limit forbids that. Something must discretize the storage. The third direction comes from a specific approach to quantum gravity that takes discreteness seriously from the beginning, deriving it from first principles rather than assuming it, building a theory where spacetime is assembled from irreducible geometric units that combine the way atoms combine into molecules. Against this, string theory and the mathematical machinery of general relativity both resist discreteness. A fundamentally granular spacetime would require rewriting physics at so deep a level that virtually nothing of the current framework would survive unchanged. These two camps have been producing competing theories for decades. Each has made genuine progress. Each has solved problems the other struggles with. Each has left critical questions unanswered. The question of whether space-time is continuous or granular is unsettled, and no experiment yet exists that can directly settle it. What is clear is that the Planck length sits at the center of the disagreement. If space-time is discrete, the Planck length is the size of its fundamental building block. If space-time is continuous, the Planck length is the scale where continuity must give way to something we do not yet understand. One camp decided to try a completely different approach entirely. They kept space smooth but replaced the point particle with something extended, something vibrating, something very, very small. And that something changed everything about how quantum gravity might work. String theory arrives at a conclusion that should sound absurd the first time you hear it. The universe has 10 dimensions. We experience 4 of them, 3 of space and 1 of time. The other 6 are real. They are present right now, everywhere around you, curled up at scales near the Planck length, invisible at every energy level science can currently reach. The reason string theory demands this is mathematical, and the mathematics is unforgiving. When physicists worked out the equations governing vibrating strings, they discovered that the theory only holds together in 10 dimensions. In any other number, a particular kind of mathematical inconsistency appears, a breakdown in the probability rules that quantum mechanics requires, the kind of breakdown that makes a theory nonsensical, spitting out negative probabilities for physical events. The only fix is the right number of dimensions, and the right number is 10. So where are the missing 6? Compactified, curled into shapes so tight that they close back on themselves at scales comparable to the string length, which sits near the Planck scale. Think of a garden hose viewed from far away. From a distance, it looks like a one-dimensional line. Walk close enough, and you see it has a circular cross-section, a second dimension wrapped into a loop too small to see from far away. The 6 extra dimensions in string theory are wrapped into loops far more intricate than a circle, with hundreds of possible curves and holes, folded geometry of extraordinary mathematical complexity. These shapes have a name. Mathematicians call them Calabi-Yau manifolds, after the 2 mathematicians who first studied them. And here is where the theory becomes both beautiful and troubling. The shape of those hidden dimensions determines everything. Every particle that exists, every force that operates, every mass, every charge, every constant of nature. These physical laws, the ones that govern the world you live in, are in string theory simply an echo of geometry you can never directly observe. Change the shape of the hidden dimensions, and you change the physics of the universe as completely as if you had rewritten reality from scratch. This means that the 6-dimensional hidden geometry, coiled near the Planck scale, is the master blueprint from which our entire physical world is read. The electron has the mass it has because of the specific curvature of a dimension curled up at a scale 35 orders of magnitude below a meter. The strength of electromagnetism, the mass of the quarks, the precise value of the cosmological constant, all of it encoded in geometry we cannot touch, cannot reach, and cannot measure directly. That is a staggering claim. It is also, in principle, a testable one. If the hidden geometry takes a specific shape, specific particles should exist in our universe, and specific others should not. The standard model of particle physics would not be an accident but a fingerprint of the compactification. The problem is that researchers have not yet solved the hidden geometry from first principles. They cannot derive from the equations alone which shape the extra dimensions took, and when physicists started counting how many possible shapes there could be, they found a number so large it threatened to turn string theory from a predictive framework into something far more bewildering. Here is the number. A 1 followed by 500 zeros. That is a rough estimate of how many different shapes the 6 hidden dimensions of string theory could take. Each different shape produces a different set of physical laws. Different particle masses, different force strengths, different cosmological constants, entirely different universes, with no resemblance to each other. String theory does not predict one universe. It accommodates every one of those possibilities with equal mathematical validity. Physicists call this the landscape. The image is apt. Imagine standing in a vast terrain with more peaks and valleys than there are atoms in the observable universe. Each valley represents a possible universe with its own physics. You are standing in one of them. String theory's equations describe the entire terrain, every valley and peak, but they say nothing about why you are standing in this particular valley and not any other. The crisis this creates is called the landscape problem, and it cuts straight to the question of whether string theory can be considered a scientific theory at all. A scientific theory makes predictions. Predictions can be tested. If the test fails, the theory is wrong. If a theory predicts every possible outcome equally, it predicts nothing. A theory that accommodates every possible universe cannot be disproved by any observation made in any universe, because every observation is equally valid in some version of the landscape. Some critics argue this takes string theory out of the domain of science entirely and into the domain of mathematics. Proponents offer a response, and it is one of the most philosophically provocative arguments in modern physics, perhaps all of those valleys are real. Perhaps every possible universe the landscape permits actually exists, separated from ours by distances no signal could ever cross. Perhaps the physical constants we observe are real but not uniquely determined by any deeper principle. They happen to have these values in our universe, the way the lottery happened to pick these numbers. In a landscape of enough universes, any specific outcome is inevitable somewhere. This proposal, known as the anthropic argument, has been deeply controversial since it was first seriously articulated. Its logic is sound in one sense. Observers can only find themselves in a universe compatible with the existence of observers, so the physical constants we measure are necessarily those consistent with our existence. But this explains the constants only by making the rest of the landscape unfalsifiable by definition. There is no way to check from inside one valley whether other valleys exist. The landscape problem is, as of today, unresolved. String theory's strongest advocates argue that a mechanism selecting our universe will eventually emerge from the mathematics. Its critics argue the theory has been granted too long a leash already. Decades of intense effort have produced no confirmed experimental prediction unique to string theory, no measurement that string theory passes, and every other theory fails. And yet, string theory's mathematical machinery, the tools it developed for calculating amplitudes and studying dualities, has turned out to be extraordinarily productive in ways nobody anticipated. It has solved problems in condensed matter physics, in nuclear physics, in quantum information theory. The theory may not describe nature at the Planck scale in the way its founders hoped, or it may be right in a form that will take another generation to recognize. While that debate continues, a completely different group of physicists built a completely different theory from completely different mathematics. They kept 4 dimensions, they kept Einstein's geometry, and they built something that changed what space means at the smallest scale. A physicist at Penn State in the mid-1980s sat down with Einstein's equations and tried something that, in retrospect, seems obvious, but had somehow never been done carefully before. He rewrote general relativity in a different mathematical language, one that had worked brilliantly for the other 3 fundamental forces of nature. The forces that govern atomic nuclei and carry electromagnetic radiation can all be described using a specific framework built from what mathematicians call gauge fields. He wanted to know whether gravity could be expressed the same way. When he finished, something remarkable happened. In the new language, the equations for gravity looked like a quantum theory waiting to happen. That physicist was Abhay Ashtekar, and the rewriting he produced in 1986 became the seed of an entirely different approach to quantum gravity, one that shared string theory's ambition but none of its assumptions. The approach came to be called loop quantum gravity, where string theory started by replacing point particles with extended strings and found that extra dimensions followed necessarily. Loop quantum gravity started by taking general relativity seriously on its own terms and asking what happens when you apply quantum mechanics directly to the geometry of space itself. The answer it returned was not extra dimensions. The answer was that space is made of something. In loop quantum gravity, space is granular, assembled from irreducible chunks of area and volume, each one a discrete quantum of geometry, the way a beam of light is assembled from discrete quanta of energy called photons. Area does not come in all possible continuous values. It comes in specific, quantized jumps, and there is a minimum non-zero value below which no smaller area exists. That minimum area is set by the Planck scale. The quantum state of space, in this picture, looks like a network, nodes connected by edges, each edge carrying a quantum number that encodes how much area is present there. The network is called a spin network, and it is the most basic description of the geometry of space that loop quantum gravity allows. Space is a fabric of quantum relationships, and those relationships have a resolution limit built into them, the same way pixels limit a digital image. When the spin network evolves through time, it traces out a four-dimensional structure called a spin foam, a history of how the quantum geometry changed, event by event, from one configuration to another. Time in this picture flows as a sequence of discrete transitions, geometry changing one quantum step at a time. This is a profound departure from both classical physics and from string theory. Space itself is not assumed to exist as a background. It is derived, constructed from combinatorial information, from the quantum numbers sitting on the edges of the network. An empty region of space is a region where no spin network edges pass. Space does not pre-exist the physics. It is made of it. Loop. Quantum gravity makes one prediction that stands in sharp contrast to anything general relativity can offer. It predicts a minimum area of roughly 1 Planck area. Below that scale, the concept of area loses all meaning. The smooth continuum of Einstein's geometry is an approximation, valid at large scales but built on a substrate that is fundamentally discrete. Whether that prediction is correct cannot yet be confirmed experimentally, but the theory's treatment of the most extreme place in the universe offers a clue that something like it might be true. And that clue comes from a question no one had seriously asked before. What actually happened before the Big Bang? The standard picture of the Big Bang has a blind spot built into it. Follow the universe backward in time, allowing general relativity to describe what happens as everything contracts and heats and compresses, and the equations lead to a singularity, a point of infinite density, a moment where temperature and pressure and curvature all simultaneously become infinite and the theory breaks down entirely. General relativity's field equations return nonsense, and physics falls silent. Most cosmologists treated this as an acceptable limit. The Big Bang was the beginning of time itself, the theory said. Asking what came before was like asking what is north of the North Pole. The question had no meaning, because the dimension in which before would exist had not yet appeared. Loop quantum gravity refuses to accept that answer. When the equations of loop quantum cosmology are applied to a contracting universe, something different happens at the moment of maximum compression. The discrete, granular structure of space does not allow energy density to become truly infinite. At the Planck density, roughly 10 to the 96th kilograms per cubic meter, a level of compression so extreme that all the mass of every observable galaxy squeezed into a single proton-sized volume would still fall short of it, the quantum geometry generates a repulsive pressure. The collapse halts, then it reverses. Physicists call this the Big Bounce. In the loop quantum cosmology picture, the moment we call the Big Bang was the moment of maximum compression in a previous collapse, the instant a contracting universe reached Planck density and bounced back into expansion. Our entire observable universe, every galaxy, every star, every atom in your body, emerged from the rebound of a cosmos that existed before ours and collapsed into the Planck scale regime where the quantum structure of space pushed back hard enough to reverse the fall. The implication is difficult to absorb. Cosmological time may not have a beginning. A sequence of universes may have preceded ours, each collapsing and bouncing, each carrying whatever physical information survived, the Planck density transit into the next expansion. The Big Bang is real, confirmed by the cosmic microwave background and by the abundances of light elements forged in the first few minutes. But the Big Bang may have been an event in a longer story, a bounce rather than a creation. As of today, the Big Bounce remains unconfirmed, a prediction of loop quantum cosmology, and checking it requires understanding what signatures, if any, a bouncing pre-universe might leave imprinted on the structure of the universe we observe. Physicists are actively looking. Some models predict faint anomalies in the pattern of the cosmic microwave background. Others predict specific properties of primordial gravitational waves. As of today, no confirmed signature has been found, but none has been ruled out either. What is worth noticing is that two theories, built from completely different starting points with completely different mathematics by completely different communities, are both pointing at the Planck scale as the place where the current story of the universe breaks open. String theory does it through the landscape of compactified dimensions. Loop quantum gravity does it through the bouncing geometry of space itself. Both are saying, in their different languages, that the Planck scale is where the ordinary narrative of physics runs out of road. The question that remains is whether they are describing the same cliff from opposite sides. String theory and loop quantum gravity could hardly be more different in their origins, their assumptions, or their methods. One requires 10 dimensions and a landscape of almost innumerable possible universes. The other keeps 4 dimensions and derives granular space from first principles. One was built by replacing particles with strings in a continuous space-time background. The other was built by applying quantum mechanics to the geometry of space-time itself and finding that the geometry does not need a background to exist in. Their communities have spent decades in genuine disagreement. At conferences, the debates have occasionally become sharp. The questions at issue are not minor refinements. They concern the fundamental structure of reality at the deepest accessible scale. And yet, underneath all the disagreement, both theories arrive at the same destination. Loop quantum gravity says that the smooth, continuous spacetime of Einstein dissolves at the Planck scale into a granular network of spin relationships. That smooth geometry is an approximation built from discrete quantum structure, and that below the Planck length there are no points, no distances, no geometric facts of any kind. String theory says that at the string length, close to the Planck scale, the behavior of spacetime changes fundamentally. 2 strings cannot be brought closer than the string length. The very concept of probing shorter distances stops working. Extra dimensions become relevant. A quantity called T-duality relates physics at distances shorter than the string length to physics at distances longer than it, making the 2 regimes physically equivalent and placing a lower bound on the physically meaningful length scale. Both theories converge on this. Below a scale near the Planck length, space-time, as currently described, ceases to be the correct description. Geometry either becomes granular and discrete, or becomes equivalent to larger-scale geometry through string duality, or dissolves into something the mathematics of the theory can describe, but the human mind cannot easily picture. The specific breakdown mechanism differs between the 2 frameworks. The fact of breakdown is shared. This convergence carries real weight. When 2 independent approaches built on different mathematics reach the same general conclusion, that conclusion deserves serious attention. The Planck length is the scale where the space-time we inhabit transitions into something else. The debate between string theory and loop quantum gravity is a debate about what that something else looks like and how it generates the smooth geometry we experience at larger scales. There is also something deeper worth noting. Both frameworks were built by people who started from what was already known and followed the mathematics rigorously without any experimental data pointing the way. Neither team designed their theory to reach this conclusion. The conclusion emerged from the equations independently, in 2 separate places, decades apart. When a result appears twice without being designed to appear, something is forcing it to appear. That question, what space-time breaks down into, has pushed theoretical physics toward places even stranger than quantum foam or granular space. Because there is one class of object in the universe where the Planck scale forces itself into practical physics, where the clash between general relativity and quantum mechanics is real and present and cannot be sidestepped by saying the energies are unreachable. These objects are black holes, and what physics has discovered inside them over the past 50 years is enough to suggest that the Planck length is the floor of everything we think we know about information, causality, and what the universe is ultimately made of. A stellar mass black hole packs several times the mass of an entire star into a region smaller than a city, and at its center, according to general relativity, the geometry curves without limit. The curvature at the core approaches the scale at which the Planck length becomes the characteristic radius of the space-time geometry itself. The quantum foam that Wheeler described theoretically in the 1950s is not hypothetical inside a black hole. In the deepest interior, it is the actual, literal physics of what is there. Every other location in the universe where quantum gravity effects become significant is beyond experimental reach. No accelerator can probe it. No telescope can see it. The Planck scale, across the entire accessible universe, is an abstraction. Something that lives in mathematics and in the logical implications of known theories. Something that points at itself from the equations without manifesting anywhere observable. Black holes are the exception. They are the only structures in nature where general relativity and quantum mechanics are both required simultaneously, where neither can be ignored, where the full weight of the unresolved conflict between the two greatest theories in physics comes crashing into contact with physical reality. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The outer layers explode outward as a supernova. The core falls inward past the point of no return. The event horizon, a spherical boundary from which nothing, not matter, not light, not information of any kind, can escape once it has crossed. Inside that boundary, space-time curves so sharply that every possible path through it, including the path of light itself, points toward the center. There is no sideways, there is no outward. There is only inward, toward the singularity, where the curvature curves until it has no further meaning. That singularity is where general relativity fails. The density becomes formally infinite. The curvature becomes formally infinite. The theory produces nonsense and stops. This is the same kind of breakdown that appears at the Planck scale anywhere in the universe, but inside a black hole, quantum mechanics cannot be treated as irrelevant. The black hole radiates. It is warm. It glows with a temperature inversely proportional to its mass, and that glow changes everything. The event horizon is where things get particularly strange. At the horizon, you are not at a high-density region. The geometry there is relatively gentle, especially for a large black hole. A stellar mass black hole has an event horizon roughly tens of kilometers across. And locally, at the boundary itself, space-time is nearly flat. An infalling astronaut would feel ordinary gravity, nothing exotic. And yet the horizon is where quantum mechanics and general relativity are in the deepest conflict, because it is the boundary across which information can flow in only one direction. For decades after Einstein, physicists assumed black holes were the universe's perfect traps. Mass falls in, nothing comes out, and whatever information was carried by the infalling matter is simply gone from the accessible universe. The black hole grows heavier. The event horizon grows larger. Eventually, nothing interesting happens at all from the outside. This picture turned out to be deeply incomplete. The correction came from Stephen Hawking in 1974, and it simultaneously solved a problem and created a much larger one. It turned a black hole from a passive gravitational trap into one of the most dangerous conceptual objects in all of theoretical physics. Hawking's calculation was built on a fact about quantum mechanics that most people have not heard stated plainly. Truly empty space is not empty. The uncertainty principle prohibits it. At every point in a vacuum, energy is constantly fluctuating, and those fluctuations are real. They manifest as pairs of particles that pop into existence together, one carrying positive energy and one carrying negative energy, and then immediately annihilate each other before any measurement can catch them. These are called virtual particles, and they are not hypothetical. Their effects have been measured in laboratories with extraordinary precision, including a measurable force between closely separated metal plates called the Casimir effect. Now place an event horizon in the middle of that vacuum. When a particle pair appears just outside the horizon, something can happen that never happens in ordinary empty space. One particle falls inward, crossing the horizon. The other escapes outward. The inward particle has negative energy, and when it falls behind the horizon, it reduces the mass of the black hole by a tiny amount. The outward particle carries positive energy and travels away from the black hole as radiation. From the outside, the black hole appears to be emitting particles. A black hole is glowing. The temperature of this radiation is extraordinarily low for any realistic black hole. A black hole with the mass of the star at the center of our solar system would glow at roughly 60 nanokelvins, far colder than the cosmic microwave background, making it essentially undetectable in the current universe. But the physics is there. Small black holes, if they exist, would be far hotter and would evaporate relatively quickly. A black hole with the mass of a small asteroid would be white hot, radiating intensely, shrinking rapidly toward its final moments. Hawking calculated the spectrum of this radiation and found that it follows a perfect thermal curve, the same kind of smooth, structureless glow emitted by a hot object with no internal features. Hawking radiation carries no information about what fell into the black hole. The radiation does not care whether the infalling matter was hydrogen gas or a library of encyclopedias or a precisely encoded quantum signal. The glow comes out identical regardless. That thermal character was recognized immediately as both a triumph and a catastrophe. The triumph: it was the first calculation in history to combine quantum mechanics and general relativity in a single coherent result and get something finite and meaningful. The Planck scale was talking, faintly but audibly, through the temperature of a black hole. The temperature formula itself contains Planck's constant, the speed of light, Newton's gravitational constant, and Boltzmann's thermodynamic constant, all four appearing together, the same family of constants whose combination produces the Planck length. The Planck scale is embedded in the physics of the horizon. The catastrophe: as the black hole slowly loses mass and eventually evaporates completely, all the information about everything that ever fell in appears to be destroyed. Every arrangement of particles, every encoded quantum state, gone permanently, with nothing but thermal noise left behind. The universe, according to this calculation, would be subtly less knowable after every black hole evaporated than it was before. Information would have been genuinely annihilated, not hidden or rearranged, and quantum mechanics has something very specific to say about that. The rule is called unitarity, and in quantum mechanics, it carries roughly the same weight as the conservation of energy. Unitarity says that the total information content of a closed quantum system is always preserved. States evolve, positions change, particles interact. But the complete description of a system at any time can always, in principle, be recovered from its complete description at any other time. Information transforms. Information rearranges. Information does not vanish. Unitarity is a precise mathematical statement that every quantum calculation ever checked relies on, with zero exceptions. Remove it from quantum mechanics, and the theory stops being predictive. Probability, amplitudes stop adding up to 1. The framework that underlies chemistry, electronics, materials science, and the entirety of modern technology collapses. If Hawking's radiation truly destroys information, unitarity is violated. Two of the most successful theories in all of science are contradicting each other in the most specific, concrete way imaginable. Stephen Hawking himself initially accepted that information was genuinely lost, that a fundamental rule of quantum mechanics broke down inside black holes, and he defended this position publicly for decades. This became known as the black hole information paradox, and it fractured the physics community. On one side stood Hawking and those who believed that black holes genuinely destroy information, that quantum mechanics requires modification at the Planck scale. On the other side stood physicists like Leonard Susskind and Gerard Hooft, who insisted that unitarity was inviolable and that Hawking's calculation must be missing something, even if nobody could identify what. The argument was not abstract. Susskind wrote a book about it. The debate ran for 20 years at conferences and in journals, with genuine heat on both sides. Eventually, developments in string theory and in the study of black hole entropy began to favor information preservation. Hawking publicly conceded the point in 2004, though the mechanism by which information escapes was still unknown. The clearest statement of the challenge came from Don Page in 1993. If unitarity holds, the Hawking radiation cannot be purely random throughout the entire evaporation. A midpoint arrives, now called the Page time, at which the radiation must subtly change character. After the Page time, each outgoing particle must carry encoded information about the interior, entangled in precise ways with all the radiation that came before. The thermal appearance must be a disguise. This is genuinely strange. It means that two photons of Hawking radiation coming out of a black hole, separated by billions of years of emission, must somehow be correlated. The early radiation and the late radiation are connected, carrying together the encoded description of everything that fell in. The information does not come out written in plain text. It comes out scrambled, hidden in the quantum correlations between particles emitted across astronomical timescales, each particle carrying a nearly undetectable fraction of the total record. Decoding it would require manipulating an amount of quantum information comparable to the total output of an evaporating black hole, an operation of incomprehensible complexity. The scrambling is real physics. Quantum chaos inside black holes, the way infalling information gets distributed across the entire quantum state of the horizon, is now a subject of active research. Physicists have shown that black holes are the fastest known scramblers of information in nature, mixing any infalling pattern into the Hawking radiation in a time proportional to the black hole's mass. The Planck scale structure of the horizon is where that scrambling ultimately happens. Something physical must happen near the Planck scale region at the event horizon to make this encoding possible. The perfectly smooth, structureless horizon that general relativity describes cannot produce it. What that something is turned out to be deeply divisive. When 4 physicists worked it out carefully in 2012, the answer they found incinerated everything. The paper arrived as a technical preprint in 2012, and within weeks it had every quantum gravity researcher arguing. The 4 authors, working at the University of California's Santa Barbara campus, had taken Hawking's result, Page's result, and the basic rules of quantum mechanics seriously all at once, and followed the logic wherever it went. The logic went somewhere terrible. After the Page time, the outgoing Hawking radiation must be entangled with the early radiation in order for information to be preserved. That is the requirement of unitarity. But quantum mechanics has another rule, one equally well tested: the monogamy of entanglement. A quantum system can only be maximally entangled with one other system at a time. It cannot share its entanglement between 2 separate partners simultaneously. General relativity says the event horizon is a smooth, uneventful boundary. An astronaut falling through it should feel nothing unusual at the moment of crossing. The horizon is defined entirely by geometry, and locally, at the crossing point, the geometry is perfectly ordinary. No walls, no drama, just a threshold. This is one of the oldest and most fundamental principles in general relativity, called the equivalence principle, and it has been confirmed by every experiment ever designed to test it. For that smooth horizon to exist, the particle pairs created near the boundary must be entangled with each other across it. One particle goes out, one goes in, and their quantum state is shared between the outside and the inside. That entanglement is what makes the crossing uneventful. It is the mechanism by which the Hawking radiation is produced. But if the outgoing particle is already maximally entangled with the early radiation, as unitarity requires after the page time, it cannot also be entangled with its partner inside the horizon. The two requirements cannot both be satisfied at once. Monogamy forbids it. The authors followed the mathematics to its conclusion. If the interior entanglement must be severed to satisfy unitarity, the horizon cannot remain smooth and uneventful. Something must exist at the horizon that represents the broken entanglement, a physical discontinuity, a boundary condition the equations demand. That something would be a wall of extraordinarily high-energy radiation, wrapping the event horizon completely. Any observer falling in would be destroyed by it instantly. The smooth crossing that general relativity promises would be replaced by annihilation at the very moment of arrival. The firewall paradox places three foundational principles in direct, simultaneous conflict. Unitarity requires information preservation. Monogamy of entanglement forbids the double quantum commitment the horizon requires. The equivalence principle demands a smooth, uneventful crossing. All three are backed by decades of experimental confirmation. All three cannot be simultaneously satisfied. Accepting any two means abandoning the third. For a year, proposals and counter-proposals arrived. Each one resolved the paradox by sacrificing something that physicists had considered inviolable. Then, in 2013, two physicists offered a resolution so strange that it either solved everything or made the mystery stranger still. Juan Maldacena and Leonard Susskind proposed that two apparently unrelated phenomena in physics are actually the same thing. The first is the Einstein-Rosen bridge. In 1935, Einstein and his collaborator Nathan Rosen showed that the field equations of general relativity admit solutions in which two separate regions of spacetime are connected by a geometric tunnel, a structure that became known as a wormhole. In general relativity, these bridges are non-traversable. The geometry collapses too quickly for anything to pass through. They are mathematical curiosities, permitted by the equations but seemingly with no physical consequence. The second is Einstein-Podolsky-Rosen entanglement, named for a different 1935 paper in which Einstein and two other collaborators described quantum entanglement as a troubling feature of the new quantum theory and tried to argue it indicated something was missing from the theory. Two particles can be prepared in an entangled state such that measuring one instantly determines the state of the other, regardless of the distance between them. This has been confirmed experimentally to extraordinary precision. It cannot be used to send signals faster than light, but the correlation is real. Maldacena and Susskind proposed that these two things are identical. Every pair of entangled quantum systems is connected by a wormhole, and that wormhole is the entanglement expressed in the language of geometry. The proposal is called ER equals EPR, after the two 1935 papers, and it is either one of the most beautiful ideas in the history of physics or one of the most audacious. If ER equals EPR is correct, the firewall paradox dissolves. The outgoing Hawking radiation and the black hole interior are not doubly entangled. They are geometrically connected, joined by a microscopic Planck-scale wormhole. The monogamy rule is not violated because the two systems are not separate at all. They are the same system viewed from two sides of a geometric bridge. The horizon remains smooth. Unitarity is preserved. The rules are not broken. They are reread. What makes this more than a clever trick is what it implies about the nature of spacetime itself. If entanglement creates geometry, then spacetime connectivity depends entirely on quantum correlations. Two distant regions are spatially connected because the quantum fields in those regions are entangled with each other. Turn down the entanglement and the geometry between them weakens. Remove the entanglement entirely and the regions become geometrically disconnected. Space tears. A physicist at Princeton tested this idea inside a controlled mathematical universe and found exactly that. Reducing entanglement between two regions of a quantum boundary theory caused the bulk spacetime connecting them to thin and eventually pinch off. Spacetime geometry is woven from quantum correlations. At the Planck scale, those correlations live at their densest. The wormholes connecting entangled systems have Planck-length throats. The fabric of space, at its smallest scale, is a network of such connections. Each one a thread of entanglement. Each thread a tiny geometric bridge. This picture is still theoretical. ER equals EPR has not been confirmed experimentally, but it offers a resolution to the firewall paradox that preserves all three principles, and it does so by suggesting that spacetime geometry and quantum information are two descriptions of a single underlying reality. It also sets up a question that loop quantum gravity has its own answer to, an answer involving stars that bounce back from the edge of existence and send messages across billions of years of cosmic time. Inside a collapsing black hole, according to general relativity, the endpoint is the singularity. Matter falls inward, density climbs without bound, and physics arrives at the same breaking point it hits in every singularity. Infinite values, meaningless outputs, total theoretical failure. The singularity is where the story ends, for the infalling matter and for every equation describing it. Loop quantum gravity offers a different ending. Recall that in loop quantum gravity, space is granular. Below the Planck scale, there are no geometric facts of any kind. Area is quantized. The smooth geometry of Einstein cannot continue into the Planck regime because there is no smooth geometry there to continue into. This means that as infalling matter compresses towards smaller and smaller volumes, it eventually reaches a density at which quantum geometry pushes back. Physicists Carlo Rovelli and Francesca Vidotto worked out what this implies for the interior of a black hole and named the result a Planck star. When a collapsing star reaches the Planck density inside the event horizon, the same quantum repulsion that stops the Big Bounce from producing a singularity stops this collapse too. The star halts. Then it bounces. It rebounds outward under the pressure of the quantum geometry, resisting infinite compression. From the perspective of the star itself, the bounce happens almost instantaneously. In the star's own time frame, it falls, compresses to Planck density, and rebounds in a period comparable to the Planck time, by far the shortest meaningful interval in physics. But the event horizon of the black hole is a region of extreme spacetime curvature, and curvature distorts time drastically. What takes a Planck time from the star's perspective can take an extraordinarily long time from the perspective of someone watching from outside. The numbers are staggering. A stellar mass black hole formed in the early universe might, from our perspective, take billions of years to complete its internal bounce. The rebound star, pushing outward against the event horizon, would eventually cause the black hole to explode outward as what physicists call a white hole, a time-reversed black hole in which matter and radiation pour outward rather than inward. The stored information, everything that fell in, would be released in that explosion. And here is what makes this observationally interesting. If Planck stars are real, black holes formed in the early universe should be completing their bounces right now or in the recent cosmic past. The explosions would produce bursts of gamma radiation carrying quantum gravitational signatures, specific properties in the radiation spectrum that would differ from any other astrophysical source. Some of the gamma-ray bursts astronomers observe today, events that flood the sky with high-energy radiation from sources billions of light-years away, could be these explosions. Old black holes, formed when the universe was young, completing a bounce that began billions of years ago, sending out a burst of radiation imprinted with the physics of the Planck scale at the moment of maximum compression. Nobody knows whether this is what gamma-ray bursts are. The signature has not been confirmed. The theory is contested. But the possibility is extraordinary. that some of the flashes crossing the sky right now are messages written at the Planck scale over 14 billion years ago, waiting to be decoded. If the universe is encoding information at the Planck length and releasing it across cosmic timescales, then the next question is what the fundamental unit of that encoding looks like. How much information fits into a single Planck-sized region? The answer to that question came from an unexpected place, and it will change how you think about the three dimensions around you. Picture a black hole sitting in otherwise empty space. You cannot see what is inside it. You cannot see what fell in, what information it swallowed, what complexity it absorbed. All you can observe is the event horizon, that one-way boundary where everything in the black hole's gravitational grip reaches the point of no return. In 1972, a graduate student named Jacob Bekenstein looked at that horizon and asked a question that no one had thought to ask. If a black hole can absorb an object with a definite entropy, and if the total entropy of the universe must never decrease, then the black hole itself must carry entropy. The second law of thermodynamics demanded it. But where would that entropy live? There are no particles inside the horizon that an outside observer can count. There is no obvious way to assign a disorder measure to an object defined by what you cannot know about it. Bekenstein found the answer in the shape of the horizon itself. The entropy of a black hole, he argued, was proportional to the area of its event horizon, measured in units of Planck area. Each patch of horizon, roughly 1 Planck length on a side, encoded exactly 1 bit of information. The bigger the horizon, the more area, the more bits, the more entropy. The volume did not matter, only the surface. This was deeply counterintuitive. In ordinary physics, entropy grows with volume. A larger room holds more gas molecules in more possible configurations, so it holds more entropy. A black hole seemed to violate this rule. All the entropy of everything it had ever swallowed lived on its two-dimensional surface, encoded at Planck scale resolution, 1 bit per Planck area. Stephen Hawking confirmed the picture 2 years later when he derived his temperature formula for black hole radiation. The entropy formula fell out of the calculation naturally, and the Planck area showed up in the denominator exactly where Bekenstein said it would. The combination became the Bekenstein-Hawking entropy formula, one of the most consequential equations in all of theoretical physics. The implication stretches far beyond black holes. Gerard Hooft, a Nobel laureate in physics, and Leonard Susskind extended Bekenstein's insight into a general principle. The maximum information that can be stored in any region of space is proportional to the area of that region's boundary, measured in Planck area units. 1 bit per Planck area. The interior volume does not determine the storage limit. The surface does. They called this the holographic principle. Every three-dimensional volume of space can, in principle, be completely described by information living on its two-dimensional surface at a density set by the Planck length. Our universe, with its 3 spatial dimensions and its seemingly inexhaustible complexity, may be a projection, a reconstruction, a hologram generated by data encoded on a surface at the deepest resolution the universe permits. The word holographic here is precise. A hologram stores a 3-dimensional image on a 2-dimensional film. Tilt the film and you see depth. The depth is real, in the sense that you experience it. The depth is derived, in the sense that it arises entirely from patterns on a lower dimensional surface. If the holographic principle is correct, the same relationship describes reality itself. The Planck length, in this picture, is the pixel size of existence. Every cubic region of space can hold no more information than its surrounding surface allows at 1 bit per Planck area. The floor of reality is measured in Planck units, and the floor is not buried inside the volume. It lives on the boundary. This was the first piece of a puzzle that would snap together more dramatically than anyone expected. Few papers, in all of science, have rerouted an entire field the way a calculation published in 1997 did. The paper was 12 pages long, written by a physicist named Juan Maldacena, who was then at Harvard, building on the holographic principle and on the mathematics of string theory. What it described was, depending on how you read it, either the most elegant proof in theoretical physics or the most outrageous claim in the history of the subject. The claim was this: a theory of gravity inside a 5-dimensional spacetime is exactly mathematically equivalent to a quantum field theory living on the 4-dimensional boundary of that spacetime. Exactly equivalent. The same physics, described in 2 completely different ways. Gravity in the interior corresponds precisely to quantum fields on the edge. One language can be translated perfectly into the other. The 5-dimensional spacetime in question has a specific geometry, a kind of negatively curved space that physicists call anti-de Sitter space. It has a natural boundary, a 4-dimensional surface surrounding it the way a soap bubble has a surface surrounding its interior. The quantum field theory lives there, with no gravity and no extra dimensions, just ordinary quantum physics in 4 dimensions. This is now called the anti-de Sitter and conformal field theory correspondence. It became the most cited paper in all of theoretical physics within roughly a decade of publication. Thousands of follow-up papers applied the framework to everything from the strong nuclear force to the behavior of materials near absolute zero. What makes it revolutionary for the Planck scale is what it says about the nature of gravity. Gravity, in this correspondence, does not exist in the boundary theory. It emerges entirely when you translate the boundary physics into the bulk language. The geometry of the interior, the curvature, the distances, the very concept of a gravitational pull, all of these arise as derived features of a quantum system that contains no gravity at all. If gravity is emergent, then the Planck scale, at which gravity becomes a quantum phenomenon, is also emergent. The boundary theory knows nothing about the Planck length explicitly. The Planck length shows up only when you translate the boundary physics into the bulk language, the way a word in one language acquires meanings when translated into another that were never explicit in the original. For the black hole information paradox, the correspondence offered an immediate result. The boundary theory is a standard quantum field theory, and quantum field theories are perfectly unitary. They preserve information, always, without exception. Because the 2 descriptions are exactly equivalent, the interior black hole must also preserve information. Whatever Hawking's calculation was missing, the information was preserved. The boundary guaranteed it. The correspondence also provided a concrete, working example of the holographic principle. The boundary was lower dimensional. The interior was derived from it. The hologram was real, at least in this particular mathematical arena. What the correspondence did not immediately resolve was how the information gets out. Knowing that a black hole must preserve information is different from knowing the mechanism by which it does so. The mechanism turned out to involve something even stranger, a direct connection between the geometry of space and the structure of quantum entanglement. The next step in understanding that connection came from a thought experiment so simple that when its author published it, several colleagues initially dismissed it as naive. It was not naive. It was one of the most important insights in modern physics. What happens if you take a system described by the anti-de Sitter and conformal field theory correspondence and reduce the quantum entanglement between 2 halves of the boundary theory? Mark van Rumsdonk, a physicist at the University of British Columbia, ran this thought experiment in 2010, and the answer he found was geometric. The interior spacetime responds. As the entanglement between the 2 boundary halves decreases, the region of interior space connecting the corresponding bulk regions begins to thin. The connection becomes a narrow bridge. Reduce the entanglement further, and the bridge pinches off entirely, splitting the spacetime into 2 disconnected pieces. Destroy all entanglement, and the interior space tears apart. The geometry of spacetime depends on the entanglement structure of the boundary. Remove the quantum correlations, and the space dissolves. Add them back, and the space reassembles. Space-time connectivity is a consequence of quantum information relationships. The threads that hold space together are entanglement threads. This was a radical conclusion. For a century, physicists had been asking how to put quantum mechanics onto a space-time background. Van Ramsdonk's result flipped the question entirely. The right question was how space-time arises from quantum mechanics. The background is the foundation of nothing. The entanglement is the foundation. Connected to this was the ER equals EPR proposal that Juan Maldacena and Leonard Susskind published 3 years later, encountered in an earlier chapter. If every pair of entangled quantum systems is connected by a microscopic wormhole, then entanglement is geometry. Full stop. Two particles sharing a quantum correlation share a space-time connection. The more entangled they are, the shorter the wormhole. The correlation and the geometry are two descriptions of one underlying fact. In 2019, physicists working on the black hole information paradox pushed these ideas further. Using a mathematical device called replica wormholes, contributions to the path integral from geometries that include wormhole handles branching through the calculation, they derived a corrected formula for how the entropy of Hawking radiation evolves as a black hole evaporates. The corrected formula, now called the island formula, showed that the entropy rises and then falls exactly as quantum mechanics demands. The information escapes. The page curve is reproduced. The calculation required that regions of spacetime inside the black hole, called islands, contribute to the entropy calculation of the outside radiation, as though they were already effectively outside the horizon. This only makes sense if the interior spacetime is connected to the exterior through quantum geometric connections of the kind that ER equals EPR predicted. The geometry and the information were one system. Taken together, these results point in a single direction. Spacetime, at its deepest level, is something that quantum information builds. The smooth, continuous, four-dimensional arena that you inhabit, where distances are definite and geometry is fixed, is a large-scale averaged version of something more fundamental. That something more fundamental operates at the Planck scale, where the entanglement threads are being woven and the geometry is assembling from its quantum substrate. Wheeler's foam, from the first section of this journey, takes on new meaning here. The churning, probabilistic geometry at the Planck scale is the assembly zone. It is where spacetime is forming out of quantum correlations. Below the Planck length, the assembly has not happened yet, and asking about distances is asking about a structure that does not yet exist. The deeper truth is assembling, and the next question is whether any of it can be tested. Far out in the universe, roughly 7 billion light-years away, two massive objects merged violently and released one of the most powerful explosions in nature. Gamma-ray bursts, like this one, last anywhere from fractions of a second to a few minutes, and in that brief window they emit more energy than the star at the center of our own solar system releases across billions of years. They are the brightest events that physics allows. They are also, it turns out, a natural laboratory for testing the Planck scale. If spacetime has a granular structure at the Planck length, high-energy photons and low-energy photons might travel at slightly different speeds. The expected difference would be unimaginably tiny, far too small to detect over any earthly distance. But if the photons travel for billions of years, any accumulated speed difference would stack up into something potentially measurable. The universe, simply by being enormous, amplifies what no laboratory could detect. In 2009, the Fermi Gamma-ray Space Telescope was watching when such a burst fired. The burst emitted photons spanning a wide range of energies. Some were relatively low energy. One was extremely high energy, carrying about 10 billion times the energy of visible light. Both sets of photons left their source at essentially the same moment. After traveling for 7 billion years, the high-energy photon arrived just 9/10 of a second after the lower-energy photons. 9/10 of a second. After 7 billion years of flight, this constraint is extraordinary. If the Planck scale structure of spacetime were producing any energy-dependent variation in light speed, that variation would need to be smaller than 1 part in 10, followed by 20 zeros, to remain consistent with this arrival time. Most quantum gravity models that predicted a first-order Lorentz symmetry violation at the Planck scale were immediately and definitively ruled out by a single observation. Progress looks like this more often than it looks like a dramatic confirmation. A null result from a carefully designed experiment is a real result. Every falsified model clears the way for better ones. The theories that survive must now explain why the effect is so small or absent entirely. Even if spacetime is discrete, perhaps the discreteness does not produce simple velocity dispersion. Perhaps the averaging over all possible quantum spacetime configurations cancels the effect for photons. Whatever the explanation, the space of viable theories narrowed dramatically. Other telescopes have followed. IceCube, buried deep in the ice at the South Pole, tracks high-energy neutrinos from astrophysical sources across the observable universe. Some quantum gravity models predict that these neutrinos should oscillate or interact differently at extreme energies if Lorentz symmetry is violated. The data so far have placed increasingly tight constraints, pushing the effective quantum gravity scale above the energies of all known accelerators. Every data point closes off possibilities. This is how physics advances without a galaxy-spanning particle accelerator. You cannot go to the Planck scale, so you wait for the Planck scale to send you signals. Some of those signals, physicists suspected, might be found in the most unexpected place, in the spatial structure of spacetime itself. Measured inside a laboratory the size of a large room, Craig Hogan spent years thinking about a question that most physicists had never considered. If the holographic principle is correct, if reality is encoded on a two-dimensional surface at Planck scale resolution, would that encoding produce noise? The boundary cannot be perfectly sharp. A holographic projection from a Planck scale pixelated surface would necessarily introduce a kind of quantum jitter into the geometry of three-dimensional space. A fluctuation too small to see with any conventional instrument, but potentially detectable with a sensitive enough interferometer. In 2014, Hogan built one. The holometer, constructed at Fermilab in Illinois, consisted of two co-located laser interferometers sharing the same physical space. Each interferometer sent laser light down a pair of arms 40 meters long, bouncing it back and forth before recombining the beams at a detector. Any fluctuation in the length of space along those arms would shift the recombination slightly and register as noise in the signal. The key was using two interferometers simultaneously. Ordinary quantum noise in the laser or detector electronics would affect the two instruments independently, producing uncorrelated readings. A genuine fluctuation in the geometry of space would affect both instruments the same way, producing a correlated signal across both detectors at the same time. A real spacetime effect would look statistically identical in both instruments. Background noise would not. The holometer ran for years, collecting data and listening for correlated noise. It found nothing matching the prediction. The holometer returned a clean answer, the simplest model of holographic noise, in which the Planck scale encoding produces a specific pattern of correlated jitter at frequencies accessible to the holometer, was ruled out. The universe does not have the particular kind of quantum geometry noise that the simplest version of holographic theory predicted. This sent theorists back to the models. If the holographic principle is real but the simplest noise model is wrong, what does the noise look like? More sophisticated models were developed, predicting different frequency signatures and different correlation structures. Each new model was more carefully specified than the last, which meant each new model was more clearly falsifiable. Science rarely progresses through dramatic confirmations. It advances through this: a prediction, a test, a constraint, a sharper prediction. Each cycle tightens the net. The holometer also reframed the question in productive ways. If holographic noise exists, it should manifest as a specific, predictable signal tied to the geometry of the experiment itself, one whose shape is determined by the physical arrangement of the measurement apparatus. The direction of the interferometer arms, their length, their relative orientation, all of these should determine what the noise looks like. This theoretical insight pushed physicists toward building experiments designed specifically for particular predicted signals rather than general noise hunts. More practically, the holometer pioneered the experimental techniques that its successors would inherit: the simultaneous dual interferometer method, the correlated noise analysis, the deep understanding of how to separate genuine spacetime fluctuations from instrumental backgrounds. All of these were developed during the holometer's operational years and passed directly into the next generation of instruments. Those instruments are now being built. The techniques are in hand. The target has been refined, and the sensitivity is increasing by a factor that, at any earlier point in the history of physics, would have seemed impossible for a laboratory-scale device. The search for the texture of spacetime is approaching its most sensitive moment yet. At Caltech in Pasadena, a new kind of experiment is being assembled. The whole thing fits inside a large laboratory room, but its designers say it can detect something no instrument in history has ever been sensitive enough to see: quantum noise in the fabric of spacetime itself, arising from the discrete structure that exists at the Planck scale. The experiment carries the name gravity from quantum entanglement of spacetime. It uses a different detection strategy than the holometer did. Rather than measuring continuous interference fringes, it counts individual photons and looks for photons that have been slightly modified, shifted in frequency, by encounters with Planck-scale quantum geometry fluctuations. The theoretical basis for what the experiment is looking for comes from a model called the pixelon. In the pixelon framework, quantum spacetime fluctuations produce a specific signal concentrated in a particular frequency range, around 17 million cycles per second, like a resonance tuned to the fundamental beat of Planck-scale structure. The experiment is built to listen for exactly that frequency. The detectors at the heart of the instrument are among the most sensitive ever built for any experiment: superconducting nanowire single-photon detectors, capable of registering individual photons with extremely high efficiency and very low noise. They need to be this sensitive because the expected signal is extraordinarily faint. The pixelon model predicts that the experiment should detect approximately 1 photon modified by spacetime quantum fluctuations every 12 minutes. 1 photon every 12 minutes. That cadence sounds slow. It is precisely the point. The photon arrival rate is predictable enough that a single unexpected photon at the wrong time tells you nothing. Accumulating those single photons over days and weeks builds a statistical picture. The signal, if it exists, will emerge as a pattern that no other source can explain. The instrument can achieve its target sensitivity roughly 100 times faster than its predecessors, thanks to the photon counting approach. A conventional interferometer must average enormous numbers of measurements over long integration times to fight down the noise floor. The photon counter, by registering individual events with precise timing, extracts information from the data far more efficiently. The team at Caltech has spent years commissioning the instrument. As of the time this script was written, the detector was approaching the sensitivity threshold at which the pixelon signal should become visible, and first science results were expected within a year or two. If the experiment detects the predicted signal, it will be the first direct measurement of quantum noise in spacetime, the first time a human instrument has heard the texture of reality at its lowest scale. If it detects nothing, it will constrain the pixelon model and every similar framework to a degree that forces fundamental revision of the theoretical predictions. Either outcome advances the story. But there is another way to test whether spacetime is quantum, one that does not require waiting for faint photon signals. It requires something even more unexpected: gravity, entanglement, and two tiny spheres floating in a laboratory. Two small spheres, each roughly the size of a grain of sand, suspended near each other inside a carefully controlled vacuum chamber. The setup looks almost trivially modest for the question it is trying to answer, but the physics of what might happen between those two spheres, if the experiment is performed correctly, could tell us whether gravity is a quantum force at all. The logic is elegant and direct. Quantum entanglement can only be generated by a quantum interaction. Two objects that interact through a purely classical force will never become entangled with each other, no matter how long they interact or how carefully you measure them. If you take two masses, place each one in a quantum superposition, let them interact only through gravity, and then check whether they have become entangled, you have a clean test. Entanglement means the interaction was quantum. No entanglement means the interaction was classical. General relativity describes gravity as a smooth, continuous geometric deformation of spacetime. It is a classical theory. If gravity is described completely by general relativity and nothing more, two masses interacting gravitationally will never entangle. If gravity is quantum, if there are gravitons and Planck scale fluctuations and quantized geometry beneath the classical description, then two masses in quantum superposition will, over time, develop quantum correlations through their gravitational interaction. This proposal, developed by physicists at University College London and elsewhere, sounds simple in principle. The experimental challenge is extraordinary. Gravity is by far the weakest of the fundamental forces. The gravitational pull between two sand grain-sized masses is vanishingly small. To generate detectable entanglement from such a weak interaction requires holding the masses in extremely precise quantum superpositions for long enough that the gravitational coupling accumulates a measurable correlation, all while maintaining complete isolation from any environmental disturbance. Any vibration, stray electromagnetic field, or thermal fluctuation would destroy the quantum superposition before it had time to register the gravitational coupling. The experimenters are fighting against the fragility of quantum states themselves. Teams at University College London and at the Delft University of Technology in the Netherlands have been pursuing this measurement for several years. As of 2025, the experiments were approaching the sensitivity required to see the signal. Assuming gravity is quantum, the next few years will determine whether the required isolation can be achieved and whether quantum superpositions can be held long enough. A positive result would be transformative. It would be the first direct experimental evidence that gravity is a quantum field, that spacetime must be quantized, that the Planck scale is genuinely the boundary between quantum and classical descriptions of geometry. It would shift the entire conversation about quantum gravity from theoretical speculation to empirical science. Finding no entanglement would be equally illuminating. If gravity does not generate entanglement, one of several radical alternatives would be required. Either quantum mechanics needs modification in the presence of gravity, or gravity is somehow classical all the way down to the Planck scale, which would force a fundamental revision of nearly everything built in the last 4 decades. The experiment does not know which result it will find. The universe does. And while those spheres approach their quantum superpositions in a basement laboratory in London, a different kind of observation is being prepared at telescopes spread across the entire planet. Pointing radio dishes from Hawaii to Antarctica to Spain, a global collaboration of astronomers assembled a single virtual instrument the size of the entire Earth. In 2019, they used it to take a picture, the first direct image of a black hole's shadow, cast against glowing gas around the supermassive black hole at the center of a distant galaxy. The image was a blurry orange ring with a dark center. To non-specialist eyes, it looked almost underwhelming, a smeared circle of light. But the physics encoded in that image was extraordinary. The shape of the shadow, the width of the ring, the brightness asymmetry from one side to the other, all of these reflected the exact predictions of Einstein's general relativity in the strongest gravitational field anywhere accessible to human observation. Since that first image, the collaboration has been improving its instruments and adding more observing stations. The angular resolution is getting sharper, and sharper resolution, it turns out, may be capable of testing something that has never been tested by any optical instrument: the predictions of loop quantum gravity. In loop quantum gravity, black holes carry the imprint of quantized geometry. The discrete structure of space at the Planck scale leaves its mark on the horizon. Calculations published in the years following the first black hole image predict that a rotating black hole described by loop quantum gravity would have a slightly different shadow shape than a classical rotating black hole. The ring would be slightly narrower. The brightness distribution would differ in subtle ways. The deviations from the classical prediction would be measurable, in principle, with a telescope network capable of achieving sufficiently high angular resolution. The next generation of Event Horizon Telescope observations, with additional stations and higher frequency observations planned over the coming years, is expected to reach that threshold of sensitivity. A careful comparison of observed shadow morphology with the predictions of loop quantum gravity and classical general relativity will become possible. Consider what this means. A Planck scale theory of quantum gravity is generating predictions about the shape of an astronomical image. The theory, whose subject is the texture of spacetime at scales a proton would describe as enormous, is producing effects detectable across billions of light-years of distance, concentrated in the most extreme gravitational environments in the universe. The path from Planck's formula in 1899 to an image of a black hole shadow is one of the most improbable intellectual journeys in the history of science. Every step required understanding something that had never been understood before. Yet here the thread leads. What the observations will find is not yet known. The images require careful interpretation. Distinguishing a quantum gravity signature from astrophysical uncertainties in the gas flow around the black hole is a technically demanding task. But the question is being asked by instruments rather than only by mathematics, and that is new. For most of the century since the Planck scale was first identified, the boundary between the known and the unknown sat at the same address, locked behind a physical barrier that forbade direct measurement. The experimental situation is shifting. The barrier remains. The approaches from the outside are multiplying, growing more precise, and converging on the same target. The picture that emerges from all of them points in a direction that would have surprised Max Planck completely. Every major framework for quantum gravity built in the last 50 years began from a different starting point, used a different mathematical language, and was championed by a different community of researchers who frequently disagreed with each other in print. String theory and loop quantum gravity share almost no vocabulary. The holographic principle and the spin network picture of discrete geometry look nothing alike at the level of their fundamental objects. The Pixelon model and ER equals EPR were developed by people focused on entirely different aspects of the problem. These frameworks agree on almost nothing, yet they all converge on the same conclusion: space-time is not fundamental. The smooth, curved, four-dimensional arena that general relativity describes, the geometric stage on which particles move and forces act, is something that emerges at large scales from a deeper structure. Below the Planck scale, the structure from which space-time emerges becomes visible, and that structure is made of quantum information. In string theory, the 6 hidden dimensions are curled up at Planck scale sizes, and the smooth geometry of the 4 familiar dimensions arises from the low energy limit of a theory whose fundamental objects are extended, information-carrying strings. The classical spacetime picture emerges only when you average over the quantum string oscillations. At the Planck scale, the averaging breaks down, and the strings themselves are what you find. In loop quantum gravity, smooth spacetime is the large-scale average of a discrete spin network. Every edge of that network carries a quantum of area. The continuous geometry of general relativity emerges when you zoom out far enough that the individual quanta wash together into a smooth surface, the way individual water molecules produce the appearance of a flowing liquid. At the Planck scale, you see the molecules. In the holographic correspondence, the three-dimensional space of the interior bulk is derived entirely from the quantum entanglement of degrees of freedom on a lower dimensional boundary surface. The geometry of the bulk is encoded in the quantum information patterns of the boundary, and those patterns operate at the fundamental resolution of 1 bit per Planck area. In every approach, the Planck length marks the same boundary. The scale at which the emergent spacetime, the large-scale average, the low-energy effective description, begins to dissolve back into the quantum substrate from which it arises. The geometry does not simply break down at the Planck scale. It was always a coarse-grained description of something finer, valid above a certain resolution and meaningless below it. This convergence across entirely independent frameworks is the strongest signal physics currently has that the picture is correct. When multiple theories built by people who disagree about almost everything else all arrive at the same place, that place deserves serious attention. The place they all arrive at is this: the universe, at its deepest level, is made of information. Matter is information. Space is information. Time, to the extent it exists fundamentally at all, appears to emerge from information. The particles and fields and geometric relationships that make up everything you can observe are what information looks like when viewed from a scale many orders of magnitude above the floor. One person saw this coming. He saw it before most of the mathematics existed to support it, because he had spent decades at the edge of physics asking bigger questions than anyone else thought to ask. Late in his career, John Wheeler began to strip his ideas down to their essential core. Wheeler had been at the center of 20th century physics for 50 years. He worked with Niels Bohr on nuclear fission before the war. He coined the term black hole, bringing that concept into common scientific usage. He spent years wrestling with the deepest problems of gravity and quantum mechanics, writing the equation that bears his name alongside Bryce DeWitt, the equation that attempts to describe the quantum state of the entire universe at once. After all of that, after a lifetime of solving problems and generating new ones, Wheeler reduced his understanding of reality to 3 words: it from bit. The it in that phrase is everything you can point to, any particle, any field, any region of space, any moment of time. The bit is information, a yes or a no, an answer to a binary question. Wheeler's claim was that every physical entity in the universe derives its existence, its properties, its very reality from information, from answers to questions, from quantum measurements, each one producing a yes or a no, and from the accumulated structure of those answers, everything else arises. This was a physical claim, made by one of the most rigorous physicists of his generation. Every particle derives its mass from the outcome of quantum measurements that could go differently. Every field configuration reflects the outcome of quantum choices at the boundary conditions. Every geometric relationship in spacetime is the record of quantum entanglement relationships among the degrees of freedom that built it. Wheeler died in 2008, before the most powerful mathematical tools for exploring this claim had been fully developed. He would have found the next decade satisfying. The holographic correspondence gave concrete mathematical flesh to the idea that space is made of information. Van Ramsdonk's calculations showed that entanglement holds spacetime together and cutting it tears space apart. The ER equals EPR proposal showed that quantum correlations and geometric connections are the same phenomenon described in different languages. The island formula showed that a black hole's interior can be reconstructed from information on the exterior once you include the right quantum contributions to the geometry. Taken together, these are the mathematical architecture of Wheeler's it from bit. They are not complete. The full theory of quantum gravity that would make these ideas rigorous and universal does not yet exist. The specific mechanism by which quantum information builds spacetime at the Planck scale in the actual four-dimensional universe with its accelerating expansion and its matter content remains to be worked out, but the direction is clear. At the Planck length, matter and space and time stop being the fundamental story. The equations stop producing numbers for geometry and start producing numbers for quantum correlations among information-theoretic degrees of freedom. At the Planck scale, the universe stops answering questions about where things are and starts answering questions about what information has been exchanged. The Planck length is the address of the deepest question the universe is willing to answer. What lives there is the raw material from which everything visible, measurable, and real is assembled. And the whole story began with a physicist who had no idea any of this was coming. Back in 1899, in Berlin, a physicist named Max Planck was doing arithmetic. He was working on a heating problem, trying to derive the correct formula for radiation emitted by a hot object. He had three constants sitting on his desk: Newton's gravitational constant, his own new constant governing quantum behavior, and the speed of light. He noticed that these three numbers could be combined in essentially one way to produce something with the dimensions of a length. He wrote the number down. He noted that it seemed philosophically significant, that it was defined by the deep grammar of the universe rather than by any arbitrary human convention. Then he moved on, because he had a heating problem to solve and no idea what the length actually meant physically. He had found the flaw of reality and thought it was a curiosity. What it meant physically would take the rest of the 20th century and the beginning of the 21st to begin to understand. General relativity revealed that at that scale, space-time curvature becomes infinite and the equations break down. Quantum field theory revealed that gravity cannot be quantized by any ordinary method near that scale, and that the infinities produced are uncontrollable. John Wheeler in 1955 realized that at that scale, space itself must be violently turbulent, a churning foam of virtual black holes and Planck-scale wormholes, the geometry fluctuating probabilistically with every possible shape at once. String theory arrived and said, below that scale, points dissolve into strings and the singularities disappear. Loop quantum gravity arrived and said, below that scale, continuous space dissolves into discrete quanta and the singularities disappear in a different way. Both theories pointed at the same scale from different directions and stopped there, unable to say what the flaw itself contained. Jacob Bekenstein found that the Planck area is the pixel size of information storage in the universe. Juan Mulder-Sena found that gravity is a holographic projection from a lower dimensional quantum system, and that three-dimensional space is derived from quantum information patterns at the Planck boundary. Mark van Ramsdonk found that cutting quantum entanglement tears space apart. The island formula found that information escapes from black holes through quantum geometric connections that only make sense if space-time connectivity and quantum information are the same thing. All of these discoveries say the same thing in different languages. The Planck length is the scale at which the emergent spacetime we live in dissolves back into its own ingredients. Those ingredients are quantum information. The universe is, at its foundation, a structure made of yes and no answers, binary quantum choices, information relationships among degrees of freedom that have no location in space, because they are what space is made of. We do not have the complete theory yet, We may never observe the Planck scale directly because the universe placed a physical lock on that resolution. Any probe, energetic enough to reach it, collapses into a black hole before it can report back. But right now, in a laboratory in Pasadena, a photon counter is listening for the specific rhythm of Planck-scale quantum fluctuations. At the South Pole, a neutrino observatory is tracking particles that have crossed most of the observable universe and comparing their arrival times and energies against quantum gravity predictions. Across a planet-spanning network of radio telescopes, an image of a black hole shadow is being refined degree by degree toward the resolution where loop quantum gravity leaves its mark. Max Planck found a number he could not understand. We have spent 125 years learning that it marks the edge of the world as we know it. The boundary between the smooth spacetime we can observe and the quantum informational substrate from which it emerges. The scale at which general relativity fails. Quantum mechanics meets gravity. Information becomes geometric, and the familiar ocean of space dissolves into Wheeler's foam. We still do not have a complete theory of what happens there. The universe appears to have placed a physical lock on that door. But the lock is made of the same physics as the door. And right now, we are building the keys.